It's not the same as your scintillating lectures.
Scintillating.
That's a college word I don't know. Scintillating.
Scintillation. Scintillation.
No. Molly and I can just make it work.
That is a scary look right there. You look like a very intense otter or a seal or something.
For her, in her case, she's a little otter. She's not a seal.
Is otter? No, is it seals? Seals do
Otters
that.
don't make that noise.
Yeah, it's seals. It's seals do that. I don't know. That's a dolphin.
No, it's a dolphin.
I don't know. Otters, they're water things. They're like waters. Otters are mermaid dogs. That's what they are.
Otters are mermaid dogs.
Huh. I was on Reddit too.
All right, who wants to come up and explain muscle contraction? Who wants to do my job?
I thought you were offering gum to everybody.
Or what?
You're not completely useless.
For the most part.
Tug of war.
Do I bring my
It
notes?
was really hard to get it through.
So whoever comes up first, and it can be partners or a group or whatever, let's just come up and name all the components of the muscles, so the actin and myosin, talk about those, describe the sarcomere, and then you can be done. And then the next person or group can come up and talk about the actual coupling slash filament.
So we're going to start at the macro level and dive in, or are we going to start?
I think you guys got the connective tissue coverings down probably, right? Endomysium, paramysium, epimysium.
It's just the fascial layers.
Yeah, we'll cover that later. Let's just do muscle contraction right now, because I think that's more complex. So who wants to come up and just talk about the myofilaments? What's that?
So like,
Are you volunteering? Thank you for volunteering. Let's all round.
Abigail!
Take my laptop because I
Absolutely. And then you can ask if you forget
Alright,
something.
I got this.
That's what it is.
Should I use the draw? Okay.
Can I use the jaw?
Alright.
I ain't got it.
Wait, you're allowed to bring your notes?
Well, I just want to look
It's not a
at
quiz.
I'm gonna like
If
spell
I was
some-
allowed to bring my notes, I would have.
I'm gonna
Okay,
spell
you
something.
be next.
Well, come help me then.
No.
You're gonna be next. It's fine. You'll be next.
Get your fucking mouth shut.
I'm allergic to chalk.
Just tell us about like
I'm so allergic. I can't go first.
how it's set up in the sarcomere.
Z-line.
The names and that stuff.
The muscle cells are like this.
Do not become an
So
art.
you're drawing a muscle cell of
Those are
like
muscle
various
cells.
muscle fibers, the
Right.
cylindrical
She's
structure.
right.
Sarcomere.
Right. And then these are
She should become your assistant.
pages. And then,
So you're drawing Z discs,
yeah, probably.
which cause that striated appearance
Yeah.
on the histological side of the muscle.
This is my histological side slide here. And then
What's the significance of the Z discs?
they're the end of the sarcomere, like the borders of the
Both,
sarcomere.
yeah. So it's the start and finish of the sarcomere, the
You're gonna
functional
allow us
unit
to
of
like
muscle,
condense.
and that's also where the actin myofilament attaches.
What color is the sarcomere?
Neon blue, I'm just kidding.
It is blue.
Like in the PowerPoint, I didn't have that in real life.
You're the professor telling me.
Oh, okay, well, it's purple. I'm just kidding.
Looks orange to me.
And then,
So tell us about it. So there's two muscle proteins, actin and myosin.
doesn't even go to the school.
Wait, I wanted to draw those.
Myofilaments. You
do
can
you want
tell
to
them
come help me draw this?
Come help her.
Do it.
Come help
Do
her.
it.
I'm bringing this just in case I fuck.
Actin myofilament.
I have the page over here. We're
Okay.
good, we're chilling, okay.
Beautiful striation.
So that's the tropomyosin.
Sorry, I'm trying to make it beautiful.
Go ahead, I'm gonna write the words of
This is AP class, like.
To make
Yeah, do different colors.
make the,
I can't tell which is which, Molly.
I'm sorry.
here, wait,
That's too bad.
make the,
Here, wait, hold on. I need like.
You
make
guys
the
are doing
active.
awesome, by the way. This is very.
Stop.
I'll just.
Can I
Okay,
guess?
so those are,
That's
that's the tropomyosin,
And then-
red. All these lids are mixed up,
I'm
it's really
gonna-
throwing me
Are
off.
those green dots the troponin?
You threw them off. What are you talking?
Whoever's drawing.
I
Alright, so
forgot
what
those
are,
parts
what
so
are,
far.
what's the actin myofilament made up of?
G-actin.
So
globular,
G-actin, okay.
Globular,
Trop-
right up.
tropomyosin.
So there's globular actin, which are the spheres, the G-actin. You link those together and you form F-actin, a fibrous actin strand. Tell us more, ladies.
Oh, look, we're good, look, here, I put color.
Oh, never mind.
You're good.
Forget that.
You're good, okay, and then what's the black one? Troponin.
Yeah, those are the.
So we have troponin. Go ahead.
Okay, so,
Oh yeah, those are for calcium.
calcium ion, the active site,
Oh,
and the tropomyosin.
and something else.
So troponin is a protein made up of 3 subunits. One binds to calcium, one binds to tropomyosin, and one binds the active site on the globular actin. Okay? And then tropomyosin is the only thing we haven't really talked about. What's the tropomyosin?
Tropomyosin, this.
It regulates interaction between active sites.
Yeah, so it's gonna cover those
It
active
covers
sites
this
on the
hole,
F-actin
but
strand.
then when it gets pulled, it opens them up
Correct.
and they're in. Active
Okay,
sites.
so do we understand oh, you guys, that's actin, do myosin real quick.
Oh, myosin.
Here, draw the word.
Try again.
I mean, it's like kind of.
That's the myosin molecule.
It's got 2 heads,
So
not
what,
one.
what do we need to know about myosin?
Shut up, Molly.
It's like tug of war.
No, we're not there yet. Tell me about myosin.
It's thick.
2 heads.
Looks like a golf club, right?
It combined to active sites.
It's got a shaft and a head, or a rod and a head. All the rods are linked together in the center, and then the heads are at either end, right?
Okay, thank you. She appreciates my job. I don't know what was so wrong the first time. I just only had one.
You only had one head.
I'm sorry. I go put them together.
They're twisted together, correct? There's 2 heads on each side. Coiled.
There's multiple.
Basically like 2 golf clubs coiled.
It's more than 2. It's a lot, right?
Yeah, they're on top, like the top of each other.
Yeah.
Those are coiled.
Not like this.
Molly, our conversation.
All right, that's good. Thank you too. That was-
Wait, are we gonna put them together or no?
Wait,
I'm gonna have
hold
somebody
up.
else do
What?
the rest of
You
it.
two don't like our
I
song?
tried
No, you
to.
guys did great.
I tried to show
Thank
how
you.
they like each other.
Not that we need to, but let's review real quick. So our 2 myofilaments are called what and what?
Actin and
Actin and
myosin.
myosin. Actin is made up at let's talk about the components at a simple level. The strand of actin is made up of what?
Globular actin.
Globular actin. You link together those G-actin, globular actin to form
Fibrous actin.
F-actin strand. It's a double helix coil of those of the fibrous actin. We have tropomyosin, which is that rope-like structure that sits in the grooves of that double helix. And then we have troponin, which is that 3 subunit molecule that's one binds to calcium, one binds to tropomyosin, one binds to active sites on the F-actin strand. Okay, so those are components of the actin molecule. Does that make sense? You know how it goes together. You could do a drawing. You got that. Okay. The other myofilament is what?
Myosin.
Myosin, and we can link together. So first off, what does myosin look like? The golf club, it's got a shaft, a rod, and then the head. We can link together those rods in the center to create multiples of these myosin myofilaments. Okay, so we pretty clear on that. And we understand that those are organized, and so if I was drawing this, I'd probably shift it this way, right? Because the rest of our drawings are in this manner, so don't get that confused. But so that the actin's bound to the Z disc, more actin on the other Z disc. So from 1 to 1, this is what's the unit called? Sarcomere. That's what shortens during a muscle contraction, right? And they're stacked up along the length of that muscle fiber. So we good with that?
Are they staggered though, or do they line up like in a straight Z in a
They're
line?
usually staggered.
Okay.
Okay. So who wants to come up and describe the kind of the actions of those myofilaments? How we're going to get an actual shortening of those sarcomeres?
Are we allowed to bring up our boats and stuff?
Yeah, you can bring up what you want. You can bring a friend. Whatever you'd like.
Alex, you want to be my friend and come up with me?
Yeah, let me do a quick review real
If you
quick.
want to use these drawings,
Since I
great. If
wasn't
you want to do another one, that's
quite
fine
last
too.
time.
You don't want to use my
I know there's.
I'm not going up there again.
Um,
I embarrassed myself once.
I'll go up there. It's not gonna be pretty, but I'll go.
That's fine.
Let's go together.
Yeah, team up.
Okay.
relaxation.
Where's the
This is the first class I haven't had to make threats to get you guys to come up here.
Okay, it's because
threats
we're all
and tricks.
friends here.
That's right.
Yeah, it's kind of a
Well,
small
usually
class.
bribery helps me.
I don't do bribes. I
You
do
give her a
threats.
Pepsi. Do you have any
I was gonna
kids?
say.
Yeah, he was a hard fucking soda.
It's
See,
October.
volunteers.
Yeah, candy's cheap and
Oh,
plentiful
I'm
right
so
now.
sorry, it's the COVID.
Alright, so what do you want us to explain, I'm sorry?
So now, tell us how these actin and myosin interact to create a shortening of that sarcomere.
So
And
they
if
interact.
you want to use these, great. If you want to do new ones.
I'm gonna use these, they're better than anything I can do. So the way that they interact is it's a big game of tug of war. They're pulling against each other, shortening. Correct? Sure. Okay, thank you.
That's not it.
Remember the word ratchet?
Yes, I hate that word.
So we need a sequence, right? So we have, first off, the actin and myosin overlap one another, right? Those sarcomeres. So tell us this kind of step by step, how those interact and how it's going to create a muscle shortening.
calcium come in at?
So.
I'm sorry?
Where's the calcium come in at?
Just the calcium.
So you'd start with calcium ions?
I would start with
What's
I think I would too.
What's that
Calcium
ATP?
comes in from
And it's
AR.
attaches-
What's that reticulum
It's
called?
ATP in there.
Sarcoplasmic
And it
reticulum. No,
attaches
muscle.
to the component
Sarcoplasmic.
that opens up the active site on the.
Here, you have it, come on.
Go with not having to.
Thank you for volunteering.
Don't look at
Don't
you, don't look at
give her a
Well, no one let me give me a shot to talk. Everyone started
hand. You
talking.
had your shot.
No, I did not. I did not.
All right, let's
I
listen.
don't wanna write nothing down.
Go
You don't
ahead.
have to write nothing
Okay,
down.
good, okay, great, so this is calcium, it's already there, correct? So once it comes in, it's like, hey, I need you to open this up, so it's opening up these little sites on here, and when it opens it up, it detaches and goes somewhere. ATB was in there while I was helping it out, and this thing right here comes in, and it does this click on there, it's like,
So it binds first, right?
right, it
Yeah,
binds,
then it
and then it
ratchets.
ratchets, that's the word.
And
then
the
it
ratchets is what's gonna slide them back.
and they come together, and then that's what shortening of the muscles happen, okay? So-
I was
That's
gonna get
basically
there.
what I
No
All right, real simplified, but actin and myosin molecules, right? So green's actin, blue is myosin, they're overlapped like this, right? So calcium, which is sequestered in the sarcoplasmic reticulum, and we'll see that today probably, gets released. The calcium ion binds to what?
Active site.
No.
No, it.
The tropomyosin, troponin.
Binds to the troponin, specifically that subunit that binds to calcium ions. When it binds, it causes the troponin to move and pulls tropomyosin out of the way, okay? Now with the tropomyosin out of the way, what is exposed on the actin?
The active site.
The active site. So with that active site exposed, what does the myosin do?
Slides right in there.
Yeah, the myosin head comes up, attaches to that active site, and then it goes through that ratcheting sequence where the head kind of cocks and it pulls the two myofilaments past each other. So, and then it's going to do that in a sequence, right? So it's going to bind, ratchet, release, bind, ratchet, release, and it will do that. Many of them will do that at the same time, and that's our analogy with the tug of war, right? Hand over hand, multiple teammates kind of doing it at various times.
So are they attached before calcium comes into the picture? Like,
No, they can't be, right?
They're not
How
at
could they
all.
be attached to an active site that's covered?
Because it's covered by the
myosin's, like,
tropomyosin.
floating.
It's not
in the
floating,
calcium.
must be
it's just
present
in
for
its
muscle contraction.
resting state, right? It's anchored
Very general.
to that M line in the middle,
Oh, okay.
just like the actin is anchored to the Z disc.
Okay.
So their structure's just sitting there.
Are their structures still held relative to each other? What through the? I mean, so you've got the Z line, you've got the Z disc, and then the M line. Is that the center? Right. So and those are ultimately connected exteriorly through sarcoplasmic reticulum. I mean, how are they not like floating? I get that there's anchored, but how are those two anchors connected to each other? Like
Those two are not connected to each other. There's a Z disc on each end, which is a connective tissue structure within the cellular makeup of the muscle. And then in the middle, you have your M line, which is another connective tissue, or you need to look it up again, or protein structure that is part of that makeup of the sarcomere. So if you want to think of an analogy, think of the sarcomere as this room. So one wall is a Z disc, that wall is another Z disc. In the middle, you can have a table, and they're connected to those structures. Right?
okay.
Does that make sense? Does that help your visualization? There's some good videos. I'll show you next time some good videos on YouTube where it kind of gives a more three-dimensional view of it.
So for the Z discs then, are there two Z discs right next to each other as like a start and an end and then a start and an end, or is it really just one on each side?
There's one on each side. So again, if we're going to use this room as an analogy, so there's a room next door, right?
Right.
So this wall as a Z disc is going to have actin connected to it in this room. And if you went next door, it'd have actin connected to it in that other room too. And those rooms are stacked up just like these are, one there, one there, one there, right? And if you moved all these walls closer together, you'd have a shortening of the building.
That was a good analogy.
Thanks. Again, there's some good videos that'll help you guys with this, but we just need to get that story down. You guys need to be able to articulate that story, right? You should be able to teach somebody who knows nothing about it, right? You could pretty quickly do that.
So then one last clarifying question. So the M line is not just like an arbitrary area that's designated, it's an actual physical structure.
Correct, and some of those the I bands and other stuff are just a space. It's
Zones,
from-
right? Yeah, okay.
And that's why I'm less concerned about
Okay, but
these are actual structures.
okay.
Okay, so we good with that?
Cool.
Okay, let's lecture about some new stuff. So let's go back and talk about resting membrane potential, which is a certain condition that exists in all these excitable cells, including muscle cells, nerve cells, and your other cells that can be stimulated by a nervous impulse, by a nerve impulse. They're all going to have a resting membrane potential, which allows them to carry out all these actions. So let's just talk about kind of a generic cell here. So these are just going to indicate my cell walls. So this is inside, outside. What do we know about the cell wall? I'm simplifying it, but tell me some things we know about it. Yeah, it has selective permeability, meaning it lets some stuff in, but not other stuff. So
Phospholipid bilayer.
yeah, small stuff. It's a phospholipid bilayer, right? You guys remember what that looks like? It's got channel proteins in it. It's got other types of proteins in it, right? Okay. It could have a sodium potassium pump, yeah, which will be important to us. So let's talk about, for a certain cell that has this resting membrane potential, let's talk about what it looks like inside to outside. So inside a typical cell that's in kind of a charged state, the inside of the cell is going to be electrically more negative than the outside. So there's a charge difference from inside to outside, meaning that the cell is polarized. So it's not at equilibrium, right? We talked about equilibrium, how stuff wants to be the same inside, outside. It's not equal, and this is because there's some negatively charged ions on the inside, more importantly, some large negatively charged proteins on the inside, okay, keeping the inside of the cell more negative than the outside. Talking chemically, there's more potassium ions inside than outside, but there's more sodium ions outside than inside. So again, this is not at equilibrium, right? This membrane is providing a barrier to keep these two gradients from inside to outside. So you had mentioned the sodium-potassium pump. There's a pump that uses ATP and uses energy to pump these molecules against their concentration gradient. Because if you just open up this membrane and let the sodium and potassium flow where it wanted to, what would happen?
Equilibrium.
Yeah, the potassium would do what?
Leak out.
Leak out until you had the same inside and outside, and the sodium would do what? Leak inside, right? But we have this membrane here preventing that. And we have that sodium-potassium pump creating that imbalance, right? Creating that resting membrane potential. That meaning that cell or that membrane has a potential to change at any moment if it's given a stimulus, right? Okay, so part of this cell wall, we talked about how there's protein channels, right? These are typically closed. Okay, so some may be specific to sodium, some may be specific to potassium, some may be specific to calcium or other ions. So let's say these blue ones are sodium channels, sodium ion channels. And these are going to be voltage gated channels, meaning they respond or change or open in response to a voltage stimulus, so an electrical stimulus at that point, okay? So if these channels open, so if we, and we've already said it, but if we open these sodium channels, sodium is going to move from outside to inside. If we open these potassium channels, potassium is going to move inside from outside, okay? So sodium-potassium pump and the negative ions have created these electrical and chemical gradients from inside to outside. That's our resting membrane potential. So now let's give this cell a stimulus. So let's say this is a nerve cell that's coming from your brain, traveling down your body and your appendages to the skeletal muscle. So let's say your brain wants to contract your bicep, so it sends an impulse through the nerve, okay? So we're just gonna say there's a general stimulus, there's a conscious stimulus to the nerves, and we'll get more into that. But so we have a stimulus at the nerve. How do we get that signal down the nerve to the muscle to cause a contraction? So that stimulus is going to change the voltage at these voltage gated channels to open the sodium channels, okay? So sodium channel opens, sodium ion, oops, sorry, wrong way. Sodium ions move into the cell, and as they do, they take their positive charge with them. So now it's flipping that polarity, and the inside is becoming more positive than the outside, right? Because we used to be more negative on the inside because of these So as it flips that, it'll stimulate the channel next to it and open it. And then sodium ions move in, bringing their positive charge, flipping the polarity, right? And then it'll affect its neighbor, and in a domino effect, that'll go all the way down the length of this nerve until we get to the muscle. Okay, does that make sense?
The
So this-
presence of sodium, of additional sodium inside sets off that chain reaction to open
Right,
additional
right,
channels.
because it takes in that positive charge and flips the polarity, and when that flips, it stimulates the next voltage gated channel in line.
Because you're not changing the polarity of the entire like cytoplasm yet, right?
Right,
You're
you're
just
doing
like,
it
it's
in
like
this distinct area.
proximity, like,
Right.
okay.
So you're doing it in that area, and it affects its neighbor, and then travels down the length of that nerve cell. So it's propagating a signal, right?
So then does that go nerve cell to nerve cell through like neurotransmitter use?
It depends. Sometimes you'll have, you can have one nerve cell stimulating the next nerve cell, and there's a synapse in between, or you can just have one nerve cell with a really long axon that's going to the skeletal muscle, which in the case of the skeletal muscle, that's the case. You have the cell body within the central nervous system, and then the peripheral nervous system has that long axon that carries that signal down to the muscle. Okay? So we've set that signal down. This is called an action potential. In the wake of this, we have to restore the resting membrane potential, right? Because if we do this and just leave the cell more positive and all this sodium inside, it can't carry out its next action potential, right? So we need to restore it. So in the wake of this, the sodium channels are going to close again. So we've stopped the inflow of sodium ions, and then the potassium channels are going to open. And again, in that sequence, following along that propagation. So now with the potassium channels open, what's going to happen? Potassium ions are going to move out. They have a positive charge. What's that going to do to the polarity of the cell?
It's gonna
Flip it again, restore the more negative inside than outside. So we've restored the polarity, but now we have a bunch of potassium outside instead of inside, and a bunch of sodium inside and outside. So we've restored the electrical gradient, but we also need to restore the chemical gradient. How do we do that? Sodium potassium pump that's gonna go use energy to pump those ions against their concentration gradient, move sodium back out, and potassium back in. So then you've restored your chemical gradient as well as your electrical gradient.
So to clarify, the chloride ions are never involved in the process other than just being there.
Yeah, not in our discussion. No. There are some. It's just note that there are some negatively charged ions as well as these large negatively charged proteins, which are making that inside more negative. As long as you don't put a bunch of positives in. Okay. So again, that's occurring in a domino effect in a sequence. That's going to propagate down. You're going to have sodium channels opening, then they close, and then the potassium channels open, and they close, and it goes all the way down. And again, this is called an action potential. So this is how we propagate an action potential down the length of the nerve to signal the muscle. How do we feel about that? That's good. Does it make sense? Okay. So it's a lot, and I don't expect you to have it memorized right now. But just keep going through that story so you do have it memorized. So next class, then I'll have you guys come up and you can tell me this story, right?
So then just to clarify, in this story, there's three characters, the potassium gates, the sodium gates, and then the sodium potassium pump. Those are the three transmembrane proteins that are involved?
Yeah.
Okay.
Yeah. And then remember your polarity, more negative inside than outside, and why that is. Remember more sodium outside than inside, more potassium inside than outside. And then be able to talk about that sequence.
It switches as it goes down and then back, correct?
What switches?
The
The polarity.
yes.
Yeah. So the polarity will flip and it'll become more positive inside. side as that sodium moves in.
Chain reaction.
Yeah, and then those close, so you don't have an influx of sodium anymore, and the potassium channel's open, and then it flips back charge-wise when the potassium moves out, right? Because you're moving positive charge either in or out on the back of sodium or potassium, and then you restore chemical gradient with the sodium potassium.
Are the sodium and potassium coming from like nutrition, like things that you eat? Or is
Sure, yeah, and all these are present throughout your body, but yeah, if you have sodium deficiency or something like that, it can mess with your nerve conduction. Okay, so we've got this generic stimulus from the central nervous system down the length of the nerve. We've propagated this action potential. So now we're at the synapse between the nerve and the muscle. Okay. So again, these are considered voltage gated channels. Just as a reminder, they open and close relative to voltage changes. So now let's go to what's called the neuromuscular junction. This is where the neuro meets the muscular neuromuscular junction. Okay. So this is a synapse. So you can have synapse, a connection from one cell to the next between one nerve and another nerve. You can have between a nerve and a muscle, or a nerve and an organ, or a nerve and a gland, some sort of effector organ. Okay. So here's our nerve that we just propagated the action potential down to. At the end of that, we have our axon terminal, so the end of that nerve. On the other side of that synapse, we have the muscle. Okay, so what is this called again? What is this synapse called? Neuromuscular junction. Okay. So we have our axon terminal, we have our muscle. In between the two is called the synaptic cleft. This is the open portion between the two cells. Within the axon terminal, we have synaptic vesicles. And contained within those synaptic vesicles, which are little containers, we have a neurotransmitter. So presynaptic terminal, postsynaptic terminal, synaptic cleft, neuromuscular junction. So we just talked about propagating that action potential down the length of the axon using those voltage gated channels. Okay, once we get to the axon terminal, we'll get to calcium ion voltage gated channels. So that propagation continues. The calcium channels will open. Calcium ions will then move into the presynaptic terminal. The calcium ions bind to these synaptic vesicles and cause them to move to the edge of the axon terminal. And then they will exocytose the neurotransmitter that's contained inside. Do you remember what exocytosis is?
Moving.
Or endocytosis?
The vesicles moving.
Yeah, so exocytosis, we're moving larger molecules to the outside. Endocytosis, we're moving them inside. But it involves the cell membrane either binding and dumping, or it's going to engulf, or endocytosis, engulf whatever the molecule is and pull it in. Do you remember that? Okay. So we have exocytosis of that neurotransmitter. That neurotransmitter in this case is acetylcholine. So acetylcholine gets dumped into the synaptic cleft. On the muscle side of things, the postsynaptic terminal, we have ligand-gated channels. So far we've talked about voltage-gated channels, which open in response to a voltage change. A ligand-gated channel opens in response to a binding of a ligand. So it's going to be more like a key into a lock, right? So this acetylcholine is going to bind to the channel, and that will cause it to open.
One more time real quick, what is the role of calcium in this as far as the vesicle is concerned?
The calcium is going to be pretty similar to the sodium. It's got a higher concentration outside than inside, so if you open up a channel specific to it, it's going to rush in and then it's going to bind and cause a change in that vesicle to dump its contents, exocytose. Okay, so we have acetylcholine bound to the ligand-gated channel. It opens up. That allows for sodium ions to move into the muscular area. Okay, so you guys see this pattern of how we move sodium and potassium and calcium and other ions in and out of the cell to create some sort of change in the polarity and results in some sort of action. Okay, so we have sodium into the cell, and we'll come back to this. We'll talk about how that's going to then lead to the muscle contraction inside the muscle. But so we've got sodium in. At that point, when the stimulus is stopped, the acetylcholine will unbind from that ligand-gated channel. The channel will close, influx of sodium stops. So now we don't want this acetylcholine just hanging out in the synaptic cleft, because then it can rebind and continue causing a muscle contraction that we haven't, that we're not asking for. So there is a membrane protein called acetylcholinesterase, ACE meaning breakdown. So acetylcholine gets broken down by acetylcholinesterase into acetic acid and choline. And then that acetic acid and choline gets pumped back into the presynaptic terminal. It gets rebound into acetylcholine and put back into the vesicles for reuse later. Okay. So now we've propagated that action potential from the nerve, well, all the way from central nervous system down the axon to the neuromuscular junction. We've propagated that signal across the synapse of the neuromuscular junction from nerve to muscle. And now we have a voltage change in the muscle that we'll see in a second causes the muscle to contract. So do we understand that?
So the presynaptic terminal, is that just another name for the end of the nerve?
Yeah, it's the end of that axon, end of the nerve.
Okay, and same for the
Postsynaptic
membrane?
terminal in this case is the muscle.
The muscle.
Do you guys want to go through that one more time?
Can you just go back to the part about basically the enzyme that breaks down acetylcholine?
Yeah, so acetylcholinesterase breaks it down into acetic acid and choline. So in the synaptic cleft, this is occurring. It's an enzyme. It breaks down that two-part chemical into its two separate parts. Those two separate parts are pumped back into presynaptic terminal, put back together, so now it's acetylcholine again, and then put back in a vesicle for use later.
If that didn't happen, would it just continuously contract? Or would it keep on getting that message?
Yeah, and that's like,
Is that like a Charlie horse?
it can be, yeah, like a muscle spasm, when the muscle's contracting, that can be a cause. You can have like low level, they think too, like a trigger point or just chronically short contracted muscles that we all kind of have. There's probably some low level acetylcholine in the synaptic cleft that's not allowing it to relax.
So the acetic acid and the choline are separate and they bind, is that correct?
They're separated by this enzyme after they've done their job as a ligand,
Okay.
and then pumped back into the presynaptic terminal, then put back together, then put back into the vesicle. Okay, neuromuscular junction, so we know how to get that action potential down the nerve, across the neuromuscular junction, and now we're into the muscle. So let's talk about some structures of the muscle cell that we haven't touched yet. So the outside cell membrane of a muscle is called the sarcoplasm. sarcoplasmic membrane. So that membrane has these invaginations called T-tubules, which are gonna go down into the cell. So if we look at the muscle here, this is where all our actin and myosin myofilaments are lined up. Within these, we have that sarcoplasmic reticulum that we made reference to, which is the container for those calcium ions. So we've got that signal across the membrane. We said sodium sodium ions come into the cell. Those sodium ions are going to enter the cell all the way through the area of that membrane, including the T-tubule. So that T-tubule allows for such a greater penetration of that sodium influx. Okay, so that sodium can affect more deeply into the muscle, causing a complete contraction. Okay, so again, these are T-tubules. Okay, so sodium comes in, sodium ions come in. They act on that sarcoplasmic reticulum to cause calcium ion release. And then what's going to go from there?
And then it binds to the tropomyosin.
Calcium
Or binds to the troponin.
ions
Binds to the troponin,
binds to troponin,
which releases tropomyosin.
moves tropomyosin, troponin out of the way, exposes active sites, myosin heads bind, ratchet, release, sliding the muscle filaments past one another, shortening the length of the muscle down the length of that fiber, shortening sarcomeres. Okay, so now we've got a signal all the way from central nervous system, down the nerve cell, across the neuromuscular junction, into the muscle. Talks about the sliding filament theory and how that muscle shortens and contracts. Okay.
So the presence of sodium releases the calcium?
Yeah, it acts on that sarcoplasmic reticulum to cause opening of those voltage-gated channels. We good with that for now?
You said sodium releases the calcium, correct?
Yeah, it opens voltage-gated calcium ion channels.
So I know that like low calcium levels can cause like heart problems, like arrhythmias or something like that. Does that mean like the cardiac muscle, the calcium's not there, so is that why the functioning, that's why the functioning problems happen? Okay.
All right, we good with this?
Yeah. Because it's the same regardless of the type of muscle, right? This is,
Yeah.
I mean, cardiac, smooth,
Yep.
skeletal, this is the same
Yeah,
idea.
they have their unique features, but the contraction is going to be
The same.
basically the same. So one thing I want to add to this, so in talking about that action potential and that flip in polarity, so if we were to graph the polarity of an action potential, so you have your resting membrane potential, which is usually anywhere from -70 to -95 millivolts. So that's your resting membrane potential. That's more sodium outside than inside, negatively charged, polarized membrane, right? So once we stimulate that action potential, the voltage is going to go up, right? Because we have all that sodium coming in, so sodium going into the cell. This phase is called depolarization. And these are in your slides. Okay. Then that's the sodium, the voltage gated sodium channels close, voltage gated potassium channels open, and then causing that polarity to go back down negative again, right? Because all those positive potassiums are leaving the cell. Okay, this is repolarization. It typically overshoots it, and we'll talk about this phase a little bit later, and then it goes back to its state because you have those sodium potassium pumps restoring the chemical gradient. You've already restored the electrical gradient by sending potassium out, okay? So this is an electrical graphing of an action potential. First phase is depolarization, second phase is repolarization. You should know what's happening to the gated channels and the ions during during depolarization, what changes to initiate repolarization, what's going on during repolarization. Any questions? Okay, that's good for today. So next time when we come to class, you should be able to tell me that whole story from